Right about now, as you watch this video, 100 trillion neutrinos are streaming through your body every second, and you don't feel a thing. These ghostly neutrinos owe their very existence to something called the weak nuclear force, or interaction, without which the sun wouldn't shine and the universe would be dark, dull, and boring. So what is this nuclear force, and why is it the unsung hero of the universe? Unlike the other fundamental forces, the weak interaction has precious little to do with pushes and pulls. What it does do is allow some particles in the right conditions to transform or mutate into other particles. This is really rare in physics. However much I might want my Honda to turn into a Ferrari, it just never seems to happen. It's this property of the weak force that enables particles to transform from one to another type that makes it so strange and so crucial. Under the right conditions, a neutron that is bound into a nucleus can decay to become a proton. But be careful, it's not really the neutron that's decaying, rather one of the quarks inside the neutron is changing its flavour to become a different quark. But this process doesn't happen instantaneously. Instead, there is a small chance that this decay or this change of flavour will happen per second. This means that if we have a great pile of nuclei, in other words a radioactive metal say, we can work out the half-life because over a given time there's a probability that half of those nuclei will decay. In a similar way, protons within inside a nucleus can also decay by a flavour change, this time leading to beta plus decay. Although these beta decays can explain the creation of some of the neutrinos that zoom through us every second, they by no means explain them all. When teaching nuclear fusion, it's kind of tempting to just say two protons join together to form a helium nucleus. But the problem here is that said helium nucleus is actually unstable. Because of this, one of the protons will undergo beta decay to become a neutron. The remaining deuterium nucleus is much more stable and can therefore undergo further fusion reactions. As you may know, stars are the factories which build up the nuclear periodic table, and without the weak interaction, this just couldn't happen. It seems the sun is therefore the source of the huge number of neutrinos that we fail to notice every second of every day. The strong force acts over a distance of about the size of a femtometer, which is roughly the size of a nucleon, like a proton. However, the weak interaction happens over much shorter distances, typically 10 to the minus 18 meters. This is because the bosons that mediate the weak force are very massive, and this means that due to the uncertainty principle, they have correspondingly short lifetimes. Even though this force is called the weak interaction, it is crucially important because it enables the fusion of nuclei to be stable, therefore building up all the elements. And of course, it provides the mechanism whereby the sun shines. It also powers a whole bunch of radioactive processes that are used in industry, for example, and also in medicine. In fact, every proton and neutron in your body has in some way been shaped by the weak force, and you're also bombarded day in, day out by the neutrinos that are created during weak interactions in the sun. The weak force then isn't simply just one of nature's fundamental forces. In many ways, it's the reason we exist at all.